All right, so let's look at another limit as x approaches infinity. Now, I don't know. Whenever I write consider, I always figure there could be something you already know about it, maybe from something in the past, and there's probably something new. I want to approach this one without just graphing it. But let's be clear, we could graph and we could look and we could kind of notice. And as I kind of said, I don't want to say we made a guess, but we noticed that there was asymptote behavior. But what if we don't use a graph? What if we just think about like input output? Now, infinity is not a number, so I can't like plug it into my calculator. I can't on my calculator do 1 divided by infinity. But I can still think about what would happen if you take the number 1 and you divide it up a lot. So that's really what this is saying. What happens if you take something like a numerator, like the number 1, and you divide it up a lot? Like what happens if you divide it 10 times, 20 times, 100 times? What happens as you keep dividing it? What value do I intend to reach? What value do I intend to reach?
I was going to say
Cool.
it should start like one, keep going closer to 0, but never reach 0.
Good. I like how you said it should get closer to 0, but never reach 0. And that's okay, because that's what a limit is. It's a value that I'm approaching. And you're exactly right. I actually never get there. Tomorrow we'll call this a recognizable expression. A recognizable expression is simply realizing that if I take something and divide it a lot, that I'm going to end up eventually getting closer and closer to 0. And that's the definition of a limit. Now, behind every problem is still a graph. And I want to look at this graph because I want you to start to realize something. Even though we didn't do the problem with a graph, let's go back and look at it. Look, when you're graphing things, and maybe you're doing it on your own, type it in, hit zoom standard. Type it in, hit zoom standard, that's zoom 6. And go from there. Okay, maybe that's all you need to do. I'd like to look at a problem like this and hope that students from some prior knowledge realize that this is a rational graph. So it's got branches. And, well, we shouldn't be surprised that it has asymptotes. In fact, the answer to this limit problem is also confirmed with the horizontal asymptote. So there's a horizontal asymptote at 0, which again, when we say that, we're talking about the same answer that we got for this limit problem. It's the same 0. I want you to get from this, I want you to start to say from this that a horizontal asymptote would be the same thing as a limit, because it is. If you think about the definition of a limit, it's an intended height. A horizontal asymptote, by its nature, is also an intended height. Even though I never get there, it's still where I'm intending to go. So we have a pretty powerful definition I'd like to give you on the first day of this lesson. Take a look at it up here. And it's saying, as I said to you in simple words, that a horizontal asymptote and a limit as x approaches infinity, okay, well, they will be the same. Again, if the limit as x approaches infinity is equal to a, if the limit as x approaches negative infinity is equal to a. So if you have a limit, then it's going to be the same as the asymptote. Okay, if you really want to make it sound simple, a limit is an asymptote. Again, a limit is an asymptote. Now, there's one little caveat to that. A limit as x approaches infinity. But some people put that in the margin, again, because it's true. A limit is an asymptote. Okay, they are the same. Now, before we go any further, just kind of make sure you're with us, because all of a sudden we started going to infinity. Nothing on that quiz you guys took, which, by the way, they were really good, but nothing on that quiz involved infinity. Okay, infinity is thinking about far to the right or far to the left. It's thinking about big numbers like we kind of have right here. So the conversation we're having right now would not relate to the assignment that you turned in, because simply the assignment you turned in did not involve infinity. Okay, but a limit is the same as an asymptote when we talk about infinity. The limit as x approaches plus or minus infinity of the sine of x over x. Can you see that? So the limit as x approaches plus or minus infinity of sine of x over x. Just kind of by the way, sometimes we talk about infinity, sometimes we talk about negative infinity, sometimes we're specific, and we talk about both sides. It can sort of vary. Honestly, I didn't mention it, but with this problem right here, the limit as x approaches infinity, yes, that means positive infinity, but if I was going to do that without the calculator, okay, you're just more generally thinking, what happens if it's a big number? Okay, in other words, the only time I'm ever going to talk to you or make you talk to me about negative infinity is if you have a graph. Because if you have a graph, then you can kind of look to the left. But this problem right here, we really didn't have a graph, so we're just kind of just generically thinking, okay, big number, 1 divided by big number is 0. This one uses the plus or minus, so let's look at a graph. Let's look at a graph of positive or negative infinity. Also, did sine of x over x sort of make you do a little double take? Like, whoa, wait, sine of x over x, I've seen that before. Well, you have. Yes, you have. By the way, it's got a trig function, so I'm going to make sure that I'm in radians, and I'm going to hit zoom trig. If you want to play along, you would do the same thing. So sine of x over x in a zoom trig looks like that. Now, maybe not real surprising. It's a graph you've seen before. I do want to give you a chance to see it again. I don't want to go too fast here because I'm kind of curious. Do you realize that even though you've seen it before, that we're not looking at the same place? So if you're kind of like, hey, isn't there a hole in the graph up there at y equals 1? Well, yes, there still is, but that's not where we're looking right now. We're looking at infinity. That means we're looking to the right, to the left. I want to show you something that we didn't look at before because we didn't have to, and that is what is going on with this graph. Now I took off the X and Y axis, bless you, I took off the X and Y axis because I want you to see the behavior of the graph. Okay, and what you're supposed to be seeing is that it seems to kind of like be going up and down. We call that oscillating. Okay, again, it seems to be going up and down as it goes around the x-axis. It's oscillating, but eventually it's kind of tapering off. Let me move this. Okay, I'll draw this side here. So it's going up and down. It's oscillating, but it's starting to taper off. Not a bad sketch to draw. What they do. Not a bad sketch to draw. But let's talk about the intended height. Let's talk about the intended height. Now, if you want to go for a little walk with me to infinity, it'll take a while, but my intended height right now seems to be bouncing around. Okay, it's oscillating. It's still bouncing around, but it's starting to dampen. It's starting to taper. It's starting to approach an intended height. Okay, what y value, what intended height is this thing kind of leveling out to? Again, you're just visually seeing it.
Zero.
It looks like it's 0, and it is correct. Now, again, if you're like, wait, why is it 0? Well, because visually we're noticing that the y value is starting to level off at the x-axis. Okay, but we took away the x-axis so you could see that. Now, I'm going to put you to the test here, and I'm kind of wondering if you're a believer. Okay, are you a believer in the horizontal asymptote? Is there a horizontal asymptote at y equals 0? Is there a horizontal asymptote at y equals 0? Are you truly a believer? What's bugging you here? What's kind of the rub? Go ahead.
That the graph crosses the horizontal axis.
So the graph crosses the horizontal asymptote? Now, I'll stand here and I'll confirm that yes, it is. Okay, now if that's bothering you, you're noticing, you're noticing the behavior, and again, I can confirm that it's true, it crosses. So again, I ask you, is y equals 0 horizontal asymptote? Are you a believer? Now, if you're like, what am I to believe in? Well, I'm talking about this definition right here. Now, look at what this definition says. If the limit as x approaches infinity equals a, for this problem, that means the limit as x approaches infinity is 0. So if it equals 0, then y equals 0 is a horizontal asymptote. So, folks, I don't want to say we lied to you, but we didn't tell you the full truth last year. Okay? I'll ask for forgiveness instead of permission right now. So we didn't tell you the whole truth. A horizontal asymptote is not actually a line that you can't cross. It's actually a limit. Listen to that again. A horizontal asymptote. It's not necessarily a line that I can't cross. It's a limit. And so this is like the real definition of a horizontal asymptote. And again, what's the definition? It's a limit. So I'll ask you one more time. Is y equals 0 a horizontal asymptote? Well, everybody in the class should say yes. Okay. Now, that's because the limit is equal to 0. Now, sine of x over x is an interesting monster because its limit can equal 0 when I go to infinity, or its limit can equal 1. Its limit can equal 1, but that's when I go to 0. We'll talk more about that, but I just want to make sure that you realize why the answer is different today. Again, because it's infinity. Let's do one more problem. And then this is definitely something that we will pick up tomorrow. Because if you're feeling a little bit like, so how do I do these problems? I'm purposely giving you a couple different things to think about. And I'm going to do that one more time. So what we got here is the limit as x approaches infinity of 5x plus the sine of x all over x. Now, we're not going to graph it. The purpose of this problem is to see if we can find the limit with like a no graphing method. As I mentioned in the other problem, you really can't plug in infinity. I'll be honest, it's kind of a waste of time to even think like this, because there's nothing you can do with this. This will be the last time you see me do this, because there's nothing I can recognize there. I can't stand here and say, oh, that's going to be like, something divided by a big number, because I don't know what the numerator is either. It just seems kind of weird. So you can't plug in infinity. What you can do is you can try to change. You can try to change the way that fraction looks. Go ahead.
Well, the sine over x is equal to 0.
Okay, so you know what that limit is. Now, that is definitely like a big part of this problem. May I ask, or just I wonder with you guys, like, what about the rest of the fraction? Does that just kind of, I don't know, does it kind of like become some unknown value? This is a good example of using some algebra. I'm sure you had a teacher call it the Hart method. If you didn't, you can call it the Hart method, because algebra would say that that fraction is allowed to be split. Now, just kind of by the way, I'm doing algebra before I do calculus. You'll hear me say that other times. It's usually a good rule of thumb. Do algebra before you do calculus. So I split this into 5x over x plus sine of x over x. Now, something smart and intelligent was said about the sine of x over x. And again, it's really the crux of this problem. Like Bryce said, he knows that the limit of that, what's the limit of that again? It's equal to, how do you know that? Yeah, but sometimes people are like, how'd you know that? So you're allowed to use like prior knowledge. You're allowed to use like a fact, because next time it's also going to equal 0. Okay, how about 5x over x? Algebra before calculus would say that that simplifies to be 5. What's the limit of 5? Well, it's always 5, even if you go to infinity. Are you with me there? The limit of 5 is still going to be 5, even if I go to infinity. And so I'm able to, with a little bit of change, I'm able to say that this limit is 5 plus 0, which of course equals 5. Now, guess what? Guess what is true about the number 5? Guess what's true about the number 5? Guess what's true about this limit? Well, you don't have to guess, right? Good. It's a horizontal asymptote. Look, I want you to be a believer in this, because this is how you actually find horizontal asymptotes. How? You find limits. So, I don't even know what this graph looks like, but I do know that there's going to be a horizontal asymptote at 5. Okay? Now, since we have a second, let's take a look at what the graph looks like. And basically we'll confirm that we have a horizontal asymptote at 5. Let's see what happens here. By the way I turned off the X and Y axis, if you're interested in random math stuff like that, second zoom is the format menu. Second zoom is the format menu where you can mess around with some of those options. But I just want to see what this graph looks like. That didn't work. What's not right here? How about like a zoom trig? Well, that didn't work. Anybody see anything? 5x plus the sine of x all over x. Oh, my window only goes up to 4, so I'm not seeing like the whole graph. Okay, I'm trying to hold this here because I think it's going to fall, but the graph does oscillate, and it's trying to get close to that asymptote of 5. Okay, it's basically very similar to the original graph. It's just that it's up at 5. Okay, so we have some other things to talk about with limits involving infinity. Tomorrow will kind of be the main day, but we'll refer back to, and especially this definition, okay, because, well, we want you to be a believer in sort of the new and improved version of a horizontal asymptote.